Okay, function key features, Unit 5, Day 2. So we're going to go over a couple things. We're going to start with critical points. So critical points are where the graph changes direction or shape. So extremum are the points where the graph changes direction. So like it's going up and then it starts to go down. So that's a direction change. Or it's going down and it starts to go up. That's also a direction change. So those are your maximums and minimums, and they can be relative or absolute. And I'll talk more about that in a minute. But then the point of inflection is where it changes its shape, but not its direction. So it's still going down, it's just changing its shape, okay? So like that point of inflection there, the graph is still going in the downward direction, it just changed its shape. That could also be a graph going up, it just changes its shape, okay? So now let's get into relative and absolute. So a point with the greatest value compared to the point around it is a relative maximum. It's also called a local maximum. So it's higher than all the points around it, but it's not the highest point on the graph, okay? And then the point that is the highest point, that is your absolute maximum, because that's the highest it will ever get. So absolute is your very highest, relative is your other maximums that are just higher than the points around them. And that's the same for minimum. You can have a relative minimum or an absolute minimum, okay? So let's go into finding these and using a graphing calculator to approximate them. So if you have a graphing calculator, I'd pull it out right now. And we're going to find our extrema for A. So first, this is an absolute minimum. And it's at 4, -5. Okay, the absolute minimum is right there. Okay, that's the lowest point this ever hits. And we could see that that's 4, -5 just by looking at the graph. I want to also do this with your calculator though. So pull out your graphing calculator if you have one, and I want you to click y equals, it's in the top left, and I want you to plug in the equation 2x squared minus 16x plus 27, and then click graph. And you should end up with a graph that looks just like that. If your window doesn't look like that, you need to click zoom 6. So zoom, let me grab a calculator. Zoom is the middle button on that top row of the gray buttons. So zoom and then 6, and that will put it back into this window right there. And then once you got that, sorry, I'm like making tons of noise. We have to go find the extrema. So I want you to push second trace and then go to minimum since this is a minimum. If this was a maximum, you would go to maximum. Okay, so you're going to go to minimum. And then you're going to end up with this little, it's like a spider looking thing. And you want that to be to the left of the minimum. So it's going to say left bound question mark, and you're going to put that little spider thing to the left of the minimum and click enter. And then you're going to put it to the right of the minimum, click enter, then click enter again, and you should end up with, it'll say minimum, and then x equals 4, y equals -5. And that's just a way to double check that our minimum is correct. Okay? We can do the same with B, and if you do that, I want you to plug those into your calculator, see if you can get those. So the absolute maximum is -1.5 and 2.9. The relative minimum, which is that middle one, is 0.3 and -4.3. Then the relative maximum is 1.3 and -2.7. So we have 3 extrema values here. Okay, and then for C, same thing, you can do this in your calculator. We only have 2 this time. We have a relative maximum at -3, -5, or relative minimum, and a relative maximum at -0.3 and 4.5. Okay, so you can use your calculator to do these, and I need you to be able to do this in your calculator. We'll go over it more in class, but. Okay, let's go to increasing and decreasing behavior. So moving from left to right, you always move left to right. That's how we read, that's how we do math. Okay, so moving from left to right, the function may increase, it may decrease, or it may stay constant. So I want you to think that like this little man is walking along this graph. Okay, right now he would be walking uphill, he'd be walking up a mountain or up whatever it may be. So when he's walking up, that's increasing. So he's increasing from -infinity clear up to -1. That's the last point that he's going to stop increasing. Then we're going to get up to the top, and now you're just walking on level ground. So we're not increasing, we're not decreasing, we're just staying constant. So he's going to stay constant from -1 to 4, and then decreasing from 4 to infinity. And decreasing is when you're going down. So increasing, think of like you're walking up a mountain. Constant is you found a level spot, and so you're just walking across, and then decreasing, you're coming back down. Okay? So give the intervals for which these functions increase and decrease. Let's look at example A. So this increases from, if we start left, right, that starts decreasing and then it increases. So our increasing interval is from 3 to infinity. The decreasing interval is from -infinity to 3. Okay? Increasing on B, this never increases. If we go left to right, that's going downhill. And then if we start up again, we're still going downhill, so that's never increasing. And it's decreasing from -infinity to -5, then the union, that U thing, then from -5 to infinity. Okay, and example C, that is always increasing, so that's from -infinity to +infinity, never decreasing. Okay? Continuity. Okay, so a graph is said to be continuous if there's no breaks or no holes in it. So if you can draw the graph without lifting up your pencil, that's continuous. If you have to lift up your pencil to draw a hole or to make a jump, that's not continuous. And when you have to, when it has breaks or holes or asymptotes, that's discontinuous. So it's continuous if you can draw it without lifting your pencil at all. It's discontinuous if you have to lift your pencil. Okay, and there's 3 different types of discontinuity. So there's infinite, and that's where you're going to have an asymptote. So you have your graph is going forever in one way, forever in the other way, and you have that asymptote there. There's a jump, so that's when you go to some point and then you jump up to a different point and then continue the graph from there. Or there's a hole, and that's called a removable discontinuity. I think that's how you say that. So there's infinite, jump, and removable. Removable is the hole. Jump is when you just jump from one spot to another spot. Infinite is when there's an asymptote. Okay? So let's determine if these graphs are continuous, and if not, we have to identify the type and location of the discontinuity. Okay? So let's look at example A. If we were to draw this, we would have to lift our pencil to draw it. So that is discontinuous. And it's a discontinuous jump at x equals -5. And I always want you to write those with your as x. Okay? For B, this is still discontinuous because we'd have to lift our pencil, and it has 2 different types of discontinuity. So it has infinite at x equals 2, because there's an asymptote right there. And then that's not a jump, that is removable. So it's removable at x equals 4. This right here, this is not a jump, this is removable. So removable at x equals 4, because remember a jump would be like example A. Example B, that's not a jump, that's removable, that's a hole at x equals 4. Okay? And then example C, that is continuous because we could draw that without lifting our pencil. Okay? Okay, last thing, end behavior. So as x moves towards positive infinity and negative infinity, sorry, I'm having a hard time talking right now. The end behavior is what's happening with our graph. Like, is the graph going to positive infinity? Is the graph going to 0? Is it approaching 1? Like, where is the graph going? So let's look at this graph to the right. As x goes to positive infinity, positive is always the right direction. So as x goes to the right, f of x is going down, so it's going towards negative infinity. Okay, and you're going to have to always write that like that. As x, arrow, goes to infinity, f of x goes to whatever it may be. So it's always as x first and then f of x. So then as x goes to negative infinity, that graph, so as x goes to the left, that graph is going up. So f of x goes to positive infinity. Okay, let's do a couple more. So let's look at example A. So as x goes to negative infinity, so that's the left direction, f of x goes to 0. So that's just approaching 0. It's getting closer and closer and closer to 0. So as x goes to negative infinity, the left direction, f of x goes to 0. Now we're going to do the right direction because you always have to do both. So as x goes to positive infinity, f of x goes to 0 as well. That's still just approaching 0. Okay, let's look at example B. So as x goes to negative infinity, that is approaching the line -3. So as x goes to negative infinity, f of x goes to -3. And then as x goes to positive infinity, f of x also goes to -3. Okay, let's look at C. So as x goes to negative infinity, f of x is going to +2. As x goes to positive infinity, f of x goes to +2 as well. Okay, I'm just going to put the answers for those last ones so you can double check, make sure you know how to get these. Please remember to take the quiz, and I will see you guys tomorrow.